Okay, let's continue solving this mixture problem. So notice I have my differential equation that we derived using our inflow and outflow rates. I have an initial condition, hence an initial value problem. So we can solve this differential equation using, pretty much any method that you've seen thus far. But since it is section 1.5, we're going to solve it using the integrating factor. And the reason we're going to use the integrating factor is because this differential equation is linear. Notice if I'm going to add this quantity, right, to both sides of the equation. So if I do that, I obtain, so I have dx dt is equal, not equal to, is, so I'm going to add, so that's going to be plus, and I'll go ahead and just write it as 3 over 300 plus t. And I'm going to go ahead and just write my x here, equals 8. And the reason I did that, the reason I have it in this specific form is because this is a standard form of a dE being linear, right? This guy is my p of x, or p of t in this case, right? And this guy is my q of t, right? Normally we have p of x and q of x, but I don't want to write p of x here because my independent variable is time and my dependent variable is x. Normally this is yx, so just be careful with the variables. So let's find our integrating factor. Okay, let's find our integrating factor. So we have a rho of t, which is equal to e raised to the integral of p of t. And so my function of t, right, is right here, this quantity. So we have, let's just write it in black here. So I have 3 over 300 plus t, right, with respect to dt. And this integral we can, let me just go ahead and work vertically here. So we have e to the, I'm going to go ahead and take out my constant. This is an intermediate step. If you want to skip this step, that's fine. Again, it depends how comfortable you are with integrating. Hopefully pretty comfortable. So here I'm going to use u substitution. I'm going to let u be 300 plus t. Therefore, du is equal to, and this is a nice one, a nice dt. So if we substitute our expression back into our integral, we have e cubed, and then I have the integral of 1 over u, and then of course these guys are exactly the same. And this is nice. We have e cubed, and if I integrate, right, this indefinite integral, I have ln of u, but our u is really 300 plus t. And technically you can, I'm going to go ahead and write parentheses here. Yes, it is the absolute value, but we know the time is positive here, so we know it's we can ignore the fact that you could put the absolute values, but it's not necessary in this case. And then this is very, very nice because we have a natural logarithm, so we definitely can use any logarithmic properties that we know. We definitely know a power rule for logarithms, which says let me just get a different color here. I can put this 3 and move it to the position of the exponent, and then we have e raised to the ln of 300 plus t cubed. And then this is very nice because remember, e and ln undo each other. They're inverse functions. So therefore our exponent rule for, or power rule specifically, for logarithms ends up with this right here. So this is our integrating factor. So we want to multiply this guy. So we want to multiply the left-hand side and right-hand side of our differential equation. Okay, so let me just move this up a little bit. Okay, so multiplying by our integrating factor results in, let's see, we have, okay, so 300 plus t cubed dx dt plus 300 plus t cubed times this quantity. Again, this is from above. X equals, and then of course times our 8. So I have 300 plus t cubed. And let's see, my integrating factor, I don't know, let's just make it this purplish. So notice my integrating factor, I multiplied it to the left and to the right-hand side of the differential equation. And normally, after multiplying by the integrating factor, you guys have noticed that the left-hand side of the equation is the derivative of a specific special product. And so this guy, let me get my black here. So this guy is really, so the book called it big D sub x, or actually in this case t. So dt, and this is really the derivative of 300 plus, so this quantity cubed times x, right, or x of t. If you want to write, if you want to write this guy as ddt, that's fine. It's the same thing, whatever you're comfortable with. And let's go ahead and, well, let's not forget the right-hand side. So this quantity cubed. Okay, so we have our differential equation. We want to find x of t. So we can integrate both sides. So I'm going to integrate and I'm going to integrate. And on your on the video presentations, make sure a couple of you omitted this step. But when you integrate, you have to tell me with respect to what variable. Well, in this case, it's with respect to t, because that's our independent variable, and then dt. So make sure not to forget the dt. So now we know, well, this is going to be gone because those are inverse operations. So let's go ahead, let me get ahead and get my black. So we are left with 300 plus t cubed times x, right? Or if you'd like to write even x of t, that's fine, to remind you what you're looking for. And so again, this is gone. And then here we can integrate. I can take out my 8. And this is very nice. So you get 300, right? You can use our power rule, raised to the 4th divided by 4 plus our constant of integration. And let's see, just continuing, I can divide both sides by this quantity here. So I have x of t equals, let's see, so we have, well, this guy, that's just 2, so 300 plus t to the 4th, all over the same quantity, but I have 3 factors, plus, of course, our c over this guy, and equals 2, right? This is just 300 plus t plus, and let's go ahead and keep our constant over, okay, so this guy, that's a cubed. And simplifying just a little bit more, I'm distributing, so I get 600 plus 2t. And, well, you can technically write this as to the negative 3rd power. So this is our solution. So this is our solution, right? An explicit solution to our differential equation. And then we're going to use, well, remember, this is a word problem, so we have to answer the question. So we go back to our question, and what was our question asking? Well, it was how much salt is in the tank after 12 minutes. So we really want to know what x of 12 is, right, where t is in minutes. We want to know that guy. But in order to determine what this numerical value is, we need to know what the constant is. of integration. And again, this was an initial value problem. Remember, we had this guy. So let me go ahead and plug that guy in. So we have, so x of t, x of 0, that's really going to be 4. 600, that is a plus sign there. Plus 2t, well, that's wonderful because that's really 0. And this is nice because our t, okay, so here, this is going to be 0, so that's just 300. So plus, okay, c 300 to the negative 3. Okay, so let's go ahead and just solve this. This is just a nice linear equation. So what do we get? Negative 596. C, we can write this as c over 300 cubed. Then we can cross multiply, and we get the following. 300, all that cubed. So then you go to your calculator, have a graphing one, and just insert that. And my calculator, I get negative 1.512, and then I have a little e to the 10th, which really means this is really negative 1.512 times the 10th times 10, and this is just scientific notation, so we need 10 zeros. Negative, okay, so 1, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not 10 zeros, 10 spaces to the right. So this is our constant of integration, and now we can definitely use that and substitute it for this guy, and then let's find our x of 12. So I'm running out of room here, so then I get x of 12 is equal to, and then again I'm just using my this guy above, so inserting 12 for t, so I get 600 plus 2 times, let's see, I have my 12 and minus, okay, and then it's c, which is really that c, 300 plus, well, t is also 12 again, and then again this is just, you're just computing a number, and then when you punch it in the calculator, you're going to get approximately 126, and let's round it to the hundredth. So x of 12, so after, our question was how much salt is in the tank after 12 minutes. Well, after 12 minutes, we have 126.2 pounds of salt. Okay, so it was a lengthy problem, but a very important application. So again, hopefully that makes sense. If you have a specific question or maybe a certain step that I did, then it was not maybe well explained, let me know and I will do another video.